Good morning. Now the next topic is the properties of haloalkanes. Properties of haloalkanes. First is the physical properties. Haloalkanes in pure are colorless, but bromohaloalkanes and iodohaloalkanes get color on exposure of light. Many of these haloalkanes, the volatile haloalkanes, have sweet smell, melting point and boiling point. These have higher melting point and boiling point than their parent hydrocarbons, because in case of methane, the carbon attached to 4 hydrogen atoms only. But in CH3Cl, one of the bond is CCl bond, which is polar in nature. And because of the polarity of the bond, CCl bond, these have more melting point and boiling point than the parent hydrocarbon. And this melting point and boiling point increases as the iodoalkanes have more boiling point than bromoalkanes, than chloroalkanes, than fluoroalkanes. Because the van der Waals force, the force of attraction, the boiling point depends upon the ionic force, that is the hydrogen bond, and also the van der Waals force of attraction. And here, as the size of the halogen atom increases, the force of van der Waals force also increases. And therefore, the boiling point of iodoalkane is more than the bromoalkane, than chloroalkane, than fluoroalkane. Generally, the haloalkanes, the lower haloalkanes are gases, and as the molecular mass increases, they becomes liquids and solids. In case of isomeric haloalkanes, for example, in case of CH3, CH2, CH2Cl, normal chlorobutane, 1 chlorobutane, and CH3, CHCl, CH2CH3, 2 chlorobutane, and CH3C, CH3Cl, CH3. These are isomeric haloalkanes. The boiling point and melting point decreases as the branching increases. In case of 1 chlorobutane, it have boiling point higher than the 2 chlorobutane, than the 2-methyl 2-chloropropane, which these three are isomeric forms. And it is because of the increasing of branching. As the branching increases, the symmetry decreases. A more symmetry gives more efficiency of packing, and therefore higher will be the melting point and boiling point. And in case of bromobutane, 1 bromobutane, the boiling point is 375, and 2 bromobutane, it is 364, and 2-methyl 2-bromobutane, it is 346. In case of dihalobenzene, the boiling point are almost same. It is in case of dichlorobenzene, the orthodichlorobenzene, metadichlorobenzene, and paradichlorobenzene. They have almost same boiling point, but the melting point of paradichlorobenzene is higher than that of metadichlorobenzene and orthodichlorobenzene, because the paradichlorobenzenes have symmetrical structure, and therefore efficiency of packing will be higher, and therefore it have more melting point than the other two isomeric forms of this dichlorobenzene. Orthodichlorobenzene have melting point 256. Metadichlorobenzene have melting point 249, and that of paradichlorobenzene, it is very high and it is 323 Kelvin. The next is the density. The density of haloalkanes are higher than that of water. The density increases as the number of carbon atom and also the number of hydrogen atom increases. Haloalkanes are comparatively less soluble in water, but they are soluble in organic solvents. Next is the chemical properties. Chemical properties of haloalkanes. Reactions of haloalkanes can be classified into three: nucleophilic substitution reaction, elimination reaction, and the reaction with metals. And the first one is the nucleophilic substitution reaction. Here, any nucleophile is the negatively charged reagent. Negatively charged reagents. Any ions or hydroxides or any ions, that is the negative charged reagents, are called nucleophiles. Nuclear seeking, positive charge seeking reagents are called nucleophiles. Here, any nucleophile can be represented as this with a negative charge. Attack halogen or X haloalkanes and substitute the halogen of the haloalkane to form RNU plus X minus, leaving the halide ions. That is, the halogen is replaced by the attacking nucleophile. There are a number of nucleophilic substitution reactions. Nucleophilic substitution reactions of haloalkanes can be summarized as, that is, haloalkanes RX, haloalkanes, example C2H5Cl, chloroethane. When it is reacts with the NaOH, here the nucleophile is OH minus, forms ROH, that is, in place of X halogen, OH substituted, alcohol is formed. That is, in case of C2H5Cl with the NaOH, it forms C2H5OH, that is the ethanol. And the next reaction with the water plus H2O, here also OH minus is the nucleophile, and on reaction forms ROH, that is C2H5Cl reacts with water, forms C2H5OH, that is ethanol. Okay. The next nucleophilic reagent is ammonia, NH3, and with the ammonia it produces RNH2, that is primary amine. If C2H5Cl chloroethane is the haloalkane, then C2H5NH2 ethanamine will be the product. If primary amine is the reagent, R-NH2, example CH3NH2, in case of R-CH3 group, methyl group is there, that is methanamine. If it is the reagent, nucleophilic reagent, the product will be a secondary amine, that is RNHR-, that is the secondary amine, example C2H5NHCH3, that is N-methyl ethanamine. This C2H5Cl, if it is the chloroethane is the haloalkane, with the CH3NH2 methanamine, it forms nitrogen methyl N-methyl ethanamine, C2H5NHCH3. And if the nucleophilic reagent is a secondary amine, RR-NH, generally represented as RR-NH, that is example C2H5NHCH3, N-methyl ethanamine. ഇവിടെ കിട്ടിയിരിക്കുന്നത് secondary amine, ഇവിടെ reagent ആയിട്ട് എടുത്തുന്നേ ഉള്ളൂ. The product will be a tertiary amine, RR-N double dash, R double dash. That is, the hydrogen is also, the secondary amine, the hydrogen is replaced by alkyl group. Tertiary amine will be the product. And for example, if C2H5Cl reacts with the C2H5NHCH3, the product will be C2H5 twice and CH3. N-ethyl and methyl ethanolamine will be the product. And if the nucleophilic reagent is silver nitrate, AgNO2, silver nitrite, the product is RNO2, that is nitroalkane. If our haloalkane is C2H5Cl, with the AgNO2, the product is C2H5NO2, nitroethane. And instead of AgNO2, silver nitrite, if the reagent is potassium nitrite, KNO2. Here, in case of AgNO2, the NO2 group, nitro group, is attached to the carbon through nitrogen. But if the reagent is potassium nitrite, the product is RONO. NO2 group is attached to the carbon of the alkyl group through oxygen. Alkyl nitrite is the product. That is, if your haloalkane is C2H5Cl with the potassium nitrite, the product is C2H5ONO. That is, ethyl nitrite will be the product. Ethyl nitrite. This type of NO2 group is a ambident nucleophile. And the next reagent is silver cyanide. If nucleophilic reagent is silver cyanide, the product is RNC, alkyl isocyanide. Cyano group is also an ambident nucleophile, and here it is linked through nitrogen, and it is called isocyanide. For example, if your haloalkane is C2H5Cl with the AgCN, the product is C2H5NC, ethyl isocyanide. Instead of AgCN, if the reagent is potassium cyanide, the product is RCN. Here the linkage is through carbon, and this type of product is called cyanide, nitriles or cyanides. For example, if C2H5Cl is your haloalkane with the potassium cyanide, it will form C2H5Cl, that is ethyl cyanide. And the next is sodium iodide. If sodium iodide is the nucleophilic reagent, the product is alkyl iodide, iodoalkane. It is the halogen exchange reaction. Preparation നമ്മൾ പഠിച്ചതാണ് halogen exchange reaction. That is, iodoalkane will be the product. That is, if C2H5Cl is the haloalkane with the sodium iodide, it forms C2H5I. Chlorine is replaced by iodine and forms iodoethane. If the nucleophilic reagent is NaOR-, sodium alkoxide. Sodium alkoxide is the nucleophilic reagent. With that reagent, it forms ROR-, ether. An example for sodium alkoxide is sodium methoxide, NaOCH3. NaOCH3 with your haloalkane, that is chloroethane, C2H5Cl, it forms C2H5OCH3, methoxyethane. It is an ether, C2H5OCH3. And the next reagent is lithium aluminum hydride. It is a powerful reducing agent, and with lithium aluminum hydride forms the corresponding hydrocarbon, haloalkane, from which the parent hydrocarbon is regained. This hydrocarbon is formed, that is, if C2H5Cl is the haloalkane you take, the product will be C2H6, the ethane will be the product. And the next is reaction with the silver salt of the acetic acid, silver salt of the acid, or COOAg, silver acetate is an example, or COOAg, the product will be an ester, R-COOR, that is ester. For example, if C2H5Cl is the haloalkane, C2H5COOCH3, if you are taken the silver salt of acetic acid as the nucleophilic reagent, the product is C2H5COOCH3, methyl propanoate is an ester. And next reagent is the metallic substituted product of metallic derivative of alkyl group. For example, alkyl magnesium halide or Grignard reagent or MgX. Example, CH3MgBr, methyl magnesium bromide. If it is reacts with the haloalkane, the product will be a higher alkane with a sum of the carbon atoms present in the haloalkane and also in the Grignard reagent, that is R dash. For example, if C2H5Cl and CH3MgBr is the reactants, the product will be C3H8 propane. C2H5Cl ile 2 carbonum CH3 ile 1 carbonum ചേർന്നിട്ടുള്ള propane will be the product. A coupling reaction takes place. Okay.